Hello, hello. Hello. Charlie was requested, and there he is. He's so beautiful. He's mutable, as we learned in 201. Charlie is a mutable data type. Why is he mutable? Because he's got all this extra skin. It makes him more malleable than mutable, but he can change. Like, he learned how to use stools to jump up onto couches and beds, which, he didn't know how to do. And it only took him like 2 months to learn how to do. So, yeah. How's everybody doing? Here we go again. That's right. Oh, it's a rat. Yeah, it's a really big rat. He actually, he's not very big. He's only like 9 pounds. And I live in Baltimore, so I've seen some rats that could give him a run for his money. Thank you. Thank you for the shirt compliment. All right, well, this begins week 2 of the online-ness. I'm gonna let Charlie hang out here. Actually, this is the better spot. All right, I'm gonna let him hang out here for a bit, and we're gonna get to it. So let's talk about cues. Oh, all right. So today we're going to talk about cues. Well, we already talked about cues. Well, we're going to talk about fancier cues. Early in the semester, I mentioned priority cues, and I said, you can also NQ and DQ based on some sort of priority value. So today we're actually going to talk about... Wait, did I change OBS? Oh, excellent. I did. Today we're going to talk about priority cues and how we actually implement them efficiently. So, Project 3 is out. It's been out now for almost a week. There's a bit more than a week remaining. You should try to be wrapping up at least your BST classes implementation, and you should be in, hopefully, debugging mode by now. If you're not there yet, it's okay. I'm just trying to give you some sense of pace so you have like goals to go for. I understand stuff comes up in life and it's easy to be distracted by things. But yeah, so I think that's if you're into debugging your BST at this point, you've paced yourself very comfortably. If you're not yet, then you might experience some discomfort in the coming week. If you haven't looked at the project at all, yes, be very afraid and nervous. I usually try to be conciliatory, but not for Project 3 and 341. You should be nervous and go look at the project description. In case you didn't catch it on Friday, I did like a bonus video. It was only supposed to be like 30 to 40 minutes, but I think it's something like an hour and a half. And I go over the project, the BST part of the project, the BST.h, the array balance part of the project. I go into that in detail. And then later I'll talk about the splay tree part of the project. There's a baby just screaming outside. Losing its mind. So yeah, we'll talk about that later. But I want you guys to focus on the BST. The BST is worth 70% of your grade. Are there no late penalties? There are no late penalties, but your project must be in 3 days after it's due or it will not be accepted, which means if they're due on Tuesdays, Wednesday, Thursday, you can hand them in on Friday and you won't get a penalty, but if you try to hand your project in on Saturday, we won't accept it. So that's good stuff to account for the wonkiness. This project makes me want to throw my laptop out the window. Yeah, so the mental anguish you're experiencing is... the growth you're experiencing, no pain, no gain, but also particularly with recursion, your brain's starting to wrap itself really deeply around recursion. So you'll have a much better understanding of it after this project than you did going in. And yeah, I can't even speak to the difficulty of that stuff. We'll do more red-black tree practice during exam 2 review. I think exam 2 is going to be a take-home exam. And we'll have to go by the honor code. I don't really know how else to do it. I'm not gonna give you guys like the lockdown browser thing or any of that other stuff. So it'll just be a longer exam. It'll be hard, and I'll have to trust you guys to be honest. And I trust 98% of you to be honest. Are you laughing at me? See, she's like, my wife laughs at me. She has no manners. Do we still have to turn them into late project folder or just the regular one? You will. I don't know, actually. I don't know. If the normal one doesn't work, you can put them in the late one, but you won't get penalized. I'll be in Discord for 45 to 60 minutes after the conclusion of this lecture, and you can ask me project questions. I'm just going to be hanging out in a chat room, and then if I need to talk one-on-one with one of you, we'll sort that out. Okay? All right. So, remember queues? What were queues? So queues were data structure that were first in, first out. And the cool thing about queues was that you can use them to store basically a line of people. We implemented them with arrays and linked lists, and they perform really well. They perform oh so very well. So sounds going on. I think my neighborhood is actively trying to distract me. So InQ and DQ are constant time. If you do a reasonable job implementing a queue, you can get them down to constant time because you're only basically just have to keep track of the first item that went into the list so that you can DQ it, and the last item that went into the list so you can put something behind it. Now, I'm going to give you an example of something that happens all the time when you're a software developer, and something I plan on discussing in greater detail in 447, but you'll be sitting around minding your software developer business, and all of a sudden, a person will appear to you, and they'll be very congratulatory at first. Oh, we loved the work you did on queues. It was really great. People go in. The first person who is in gets DQ'd. It works wonderfully. We're really, really happy with it. And here's the thing, though. Here's the thing. We really would like it. Here's Charlie's the developer. Charlie, we'd really like it if you could change the queue from being first in, first out. This is very similar. It's still going to be a line. But every person who goes in the queue, they're going to use side. Every person who goes in the queue is gonna have like a priority, and I said earlier in the class, this is kind of like when you go to the airport and they're like, oh, Delta Platinum Gold Sky Miles Experience Priority person who's better, you get to board now, right? So you have all these people with different priorities, and we want the person with the highest priority to come out of the queue first, not necessarily the first person who gets there. So you could roll up just before boarding's called, after, the whole entire rest of the plane is there. But if you're the, ultra gold plated platinum cord aluminum monstrosity, whatever thing, you get to go in first, and you get to have all the fancy drinky drinks and all that other good stuff. So that your manager comes to you and says, oh, so we just want that, right? That's gotta be easy, right? You have a queue, and we just want to make it so the people with the highest priority get to the front of the queue. That should be easy, right? You just publish. So for the next couple classes, we're going to talk about why that's not as easy, and also how do we solve that problem efficiently, right? You can solve the problem inefficiently pretty easily. Just put all the people in a list, and then every time you go to DQ, you just go find the person with the lowest priority or the highest priority, and that would be N. When you say, well, I'll put them in a sorted list, oh, okay, well then that gets me log N, but we can do better. Somewhat. Alright, so priority queues. Priority queues kind of have a map flavor to them. Priority queues, data goes in and it has like a priority associated with it. So with maps, you have keys and values. So each bit of data, the value has a key associated with it that you use to access that data. And then with priority queues, you have a priority assigned to the value, which determines how quickly it's able to leave the queue, essentially. Priorities are typically numeric, but they can be anything as long as you can define a comparison function on them. So you could have a dog object, and that could be your priority, and then you just have to be able to compare two dog objects. So maybe you would look at their cuteness property to determine their priority, in which case, yeah, here's our MVP, because this guy, woo, he's cute. First in, never out. Yeah, bad. I'm looking for questions. Okay. It's just Jabba, which is good. Okay. Keep chatting up the chattables. All right. So, in a normal queue, DQ returns the oldest item in the queue. In a priority queue, it's the highest priority item. Why would we use this? I mean, yeah, you could use them for airlines, but bandwidth management, so to determine what kind of traffic gets priority on a particular network. AI state space search, so if you're trying to consider all the moves in a chess game, first of all, you want to be, all of the things that you write, you want to be really efficient because there's going to be a lot of ground to cover. And so if you're looking at all the possible moves you're going to make, you would want to prioritize them by how good the resulting board state looks. So a priority queue is a very efficient data structure for you to be able to take a bunch of moves and then put them in a queue for which ones you might want to like think about a bit more. Also sorting. One of the optimal sorts is uses a priority queue. Very trivially, actually. It's if you have a priority queue, you can write a sort really easily. How? Put everything in the priority queue, and then dequeue everything out of the priority queue. Done. Right? Because they'll dequeue in priority order, so you have your sorted list coming out. It's cool. All right. How to implement a priority queue? The linked lists? Dynamic array? Those are usually our two choices. We keep it sorted. How much sorting do we do? Do we leave it unsorted? How do we do this? What are and then what are our performances, right? So I'm gonna give you guys a few minutes, discuss in the chat, Discord, YouTube chat, wherever you're at. Maybe you have some friends on the phone. Maybe you're having a 341 party and watching the lecture together, eating some popcorn and sitting on Google Hangouts. I don't know. But discuss amongst yourselves, how would you implement a priority queue? So we did a queue with a normal queue with a linked list or a dynamic array. And it turns out we're always going to use a linked structure or a dynamic array. So how do we do it? And then how do we do it efficiently? Or is there something else we could use? So I'll give you guys a moment there to consider while Charlie and I hang out. Priority queue is like class warfare. Yeah. The bourgeois. Parties are officially illegal. I meant an online party, not like an in-person party. Like there's plugins that let you watch like YouTube videos synchronously with other people that you're like on Discord or Skype or whatever with. So it's a way to have fun without being in the same room as someone. Okay. All right. So linked list, how do we do that? Well, if we want to be able to efficiently get the person with the highest or lowest priority. So it turns out it depends on what you think of. It depends on what the priority means, right? You could have a priority where a low priority means that that's the first person you want to DQ or the first bit of data, or you could have it that the highest is the person that you want to DQ. It doesn't really make a difference in our implementation. We're just going to swap a greater than or less than sign. This is a big deal. In fact, if you use function pointers, you can supply that comparison, and then the data structure really doesn't care. So if I had a linked list, I could keep the element that I'm going to DQ next at the front, and I could keep the whole thing sorted. It's nice. Same with a dynamic array. They'd both be the same. The problem is, though, my insert could be very slow. My insert could be linear, right? Because, well, no. My insert could still be... Well, actually, my insert's linear because either I'm doing a binary search on an array, and when I find the spot, I have to shift everything to the right, or I'm using a linked list that I can't use a binary search on because you can't get right into the middle of a linked list. Wait a minute. We have a linked structure. It's basically a binary searchable linked list. It's a balanced binary search tree or a binary search tree. So what if we used a binary search tree? What would our So if we used a linked list or a dynamic array, in queue would be linear, right? But then DQ would be constant time, which is pretty good. So then what about a binary search tree? Well, I can insert values into a binary search tree in logarithmic time. So that's good. Yeah, why not use a tree? Yeah, I can do so. So yeah, I can put it in the balanced binary search tree. So then my insert is logarithmic. Then what does my DQ do? Where is the value I want? Yeah, of course it's a tree. Where's the value I want in a binary search tree? If I want the largest value, where do I look in the tree? Look at these kitties. It's a heap of kitties. Okay. Going to Photoshop. Right here in Photoshop. All right. So if I have a balanced binary search tree, right, and I made it. Whoa, I'm having struggle times. Where's the value that I want when I DQ? If this thing is a priority queue, where's the thing with the highest priority? The farthest to the right. Yes. Now, a lot of you guys, this is something to be careful of on an exam or just, when you're thinking about trees and stuff like this. Which one of these is actually farthest to the right? So, like if I do this. So it turns out, like visually, it's tempting to say it's this one. It's actually this one that's way up near the top, right? Because it's everything down below it is less than it. So it's that one. So when I DQ, I'm going to go grab that value. And I'm going to remove it from the tree. And so what will the performance of that be? For a balanced binary search tree, it'll be big O of log n. So I get log n in queue and log n DQ. Nice. We can do better, kind of. Sketchbook is so much better than Photoshop for this. I'll have to check it out. I believe you. I'm very new to this, so I'll have to thank you for the suggestion. All right, cool. All right, so okay. So instead of a balanced binary search tree, let's make a heap. That sounds awesome. Wait, did I switch back to Chrome? Did I do it? I did. Okay. I have my stream like in my phone and it's lagged. So I'm like, So, we can do better than a balanced binary search tree. Ooh, this is going to be fancy. This is going to be new and exciting, this thing that we're calling a heap, right? I mean, this slide is promising that a heap is basically a pile of tabby kittens. Seems pretty great. That's a big... I'm pretty hyped for this heap. Ooh! It's a binary tree. They're binary trees. Yeah. Yeah, they're just... It's more binary trees. But they are... we're going to be talking about a min heap or a max heap today. And they are complete binary trees. The key at each node is smaller than all of its descendants. That gives us a min heap, meaning that the smallest value is the root. And the heap is optimally stored in a dynamic array, like a vector. Ooh. Also, I think we can squeeze... no. Can we? No. Sorry. It's stored in a dynamic array like a vector. Why? I quit. Oh my gosh, I've been deceived. I know. I walked you guys all in to some sort of scary situation. Why are we storing the tree in an array? Why? I should rework these slides so I don't even tell you. And I say like, well, where should we store the tree or something like that? Because that's more exciting. That's more like, well, what is the mystery? And these birds are going bonkers. All right. So why in an array? So let's look at it. So we have we're going to call it the heap order property. So we had the height balance property for AVL trees, and then we had the red-black tree properties. The heap order property is each node, this is paraphrasing, each node is each node's descendants dance? I don't know. Each node descendants are all, I would know if I typed it, I think it's dance, are all less than it. And we're talking about key value for this. So that's the heap order property. So what we're saying, so for AVL trees, we're talking about keeping the tree balanced. We have the binary search tree ordering property. So this is versus. Ooh, I switched colors. Can I switch them back now? I didn't mean to do that. How did I do that? Oh, I'm so bad at this. I think this does it. Yeah, okay. Versus, this is versus the binary search tree ordering, where each node, this one has a key. Everything in this right subtree is greater than that key, and everything in this left subtree is less than that key. For a heap, this thing has a key, and then everything below it, both subtrees, all of the values and everything up here, for a max heap, all of these values are less than k. So in a binary search tree, I know. We're learning a new order property. I know, I like the other one too. We gotta move on from it eventually. Okay. I know. Your commentary is recorded and will be considered. Alright. So if this were a binary search tree, the root would have everything on the left-hand side of it. But in a heap, the root has all of the key values underneath of a particular node are great or less than it. And that's true for all of the nodes in the tree. So if I go from the root, if I start at the root and I go down to any leaf, I'm going to be looking at values descend for all root leaf paths. F for Charlie. You think Charlie's hungry? Charlie's always hungry. He's salty about the trees too. Yeah, he's like, I want to move on to a different data structure. Yeah. Anyway, it turns out we're going to be just doing arrays and link structures all semester, but I've never really missold that. All right. I know. We'll get to them. I know. You like the efficiency. Oh, well, that's just not cool. All right. Say goodbye to Charlie. He wants to go. He just wants to lay on the couch. There he goes. Shake it off. There he goes. He's walking right over to the couch. So I can't blame him. I'm not as comfortable as a couch. Okay. Charlie is all-knowing. So they're binary trees. They're not binary search trees. They're just binary trees. They're complete, and then they have the heap order property. So we're also storing them in an array. So why? Why are we storing them in an array? Why? Wait, so both right and left children are correct. Atreus. Both left and right children of a node have key values less than their parent. Charlie's I want revenge. Oh, Jules, what is this? Are you trying to jump on there? Misbehaving cat. So yeah. So why do we use an array? Back to Photoshop. So we're back in Photoshop. I'm gonna grab a new thing. So let's draw a binary search tree on the left-hand side. And let's draw a max heap on the right-hand side. Okay, and we'll put the values 1 through 10 in. So for BST, it would be 5 would be here, then 3, then 4, then 2, then 1. Then over on the right-hand side, we'll get our buddy 7, and then 6, and then 8, 9, and 10. It's not very balanced. We would want to balance these, but we're not doing that anymore. Over here, for a max heap, 10 would be at the top. Then I could have... well, the thing, it has to be complete. So I'm just going to do 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Like that. So that's a max heap. We make it an array so we can access a specific node. I like that. Yes, Bradley. Which node? Where do we want to access it? So I'm going to make another one. So then the question is, how do we add stuff to our max heap? So say I have 17, 15, 8, 1. Let me do this proper. 1, 12, and 9. All right? And remember, we have the heap order. I keep doing that. We have the heap order property. And we also require that the tree is complete. The node at the top. We can always get at the node at the top. So why an array? There's another node that we care about. We know that the min-max is always at the front of the array. Yep. But what other node do we care about besides the top node? If I'm using a linked tree representation, I can always get to the node at the top in constant time. So one of the things is if you remember back, what's interesting about having a complete tree in an array? So let's look at the indices of these. This would be index 1, 2, 3, 4, 5, 6. Right? So the interesting thing about a complete tree being stored in an array is that it fills the array left to right. If I want to add a node to a tree and keep it complete, where do I put it? Where would 16 go? Well, that's a good question. It couldn't be a leaf, right? Because 16 is greater than all the leaves. We'll work out that in a second. Doesn't matter which number's on the left or right. We don't care. Just as long as that they're less than their parent. So how do I insert something into this tree? Let's figure it out. Where would 16 go? Well, so this is the puzzle I'm going to give you guys to work out. And I'm going to give you a couple hints. And I really would like you guys to work out this puzzle. If you're watching this after the fact, pause the video and really try to solve the following question I'm going to give you. And if you're here live, I'll give you guys plenty of time to work on this. Usually this is where I would walk around the room, but I'm just going to watch the chat and hopefully answer questions as they come in. It's really, really a good exercise to figure out how to do this. So how do we insert into this heap? And the answer must be log n. How do we remove, or rather not remove, how do we dequeue? And the answer must be log n. How do we get rid of stuff? And remember when you're thinking about this, we have these two properties over here. After you do an insert, the heap order property must be maintained and the tree must be complete. And telling you that this is stored in an array is a clue. It's not even so much of a constraint as a clue. Because if I asked you to do this and I didn't tell you it was in an array, you would be very confused. Well, would you? Yeah, you'd be confused. It's much harder to do in a link structure. Replace 8, insert 8 again. If we had nodes 15 and 8, we would need to compare an insertion of node 1 to tell where to insert it under. I don't know what it is. 15 and 8, we would need to compare an insertion of node 1 to tell which one we inserted under. Let's think about this. Discuss. I like the discussion you guys already have going. How do we maintain the heap order, and how do we maintain the completeness? And I'll give you your first hint very soon. In fact, we'll put it down here. Hint number 1. Wow, that just looks like a box. Ooh. Hint number 1. Will there be a second hint? Maybe. Can you insert 16 at index 2? You could, but what do you do with 15? And move everything over 1. Oh, I have I've never heard anyone suggest that. So the suggestion is, well, if we're inserting 16, just for our example, if we insert 16, the suggestion was put it in an index 2 and then shift everything over. So then 16 would be over here, 8 would be down here, 12 would be down there, and then 9 would be here and 1 would be here. That would technically be okay, but what if we inserted... you can actually break it. There's a counter example. All right, hint number 1. Keep it complete first. So I think usually in this semester, people kind of get their priorities a little crooked because you guys have spent so much time practicing figuring out where in a tree a node belongs and then dealing... Well, I mean, it's just also, that's how all the other trees work, right? That we've dealt with thus far, is you figure out where the tree belongs, where the value belongs, and then you try to surgery the tree to make it shaped correctly. So what I'm going to tell you now is do it the opposite way. Put the new value in so that we maintain completeness, and then try to fix any problems that causes. That's actually probably hint 1 and all of them, because it's a real good hint. So, but then the question is where? Where does it go? How do I find where the node should go to keep the tree complete? And then how do I fix it? And is whatever you come up with log n? Oh yeah, and this shifting thing does not work. Let me see if I can come up with a counterexample. But think about the how do I keep it complete? Come up with a counterexample. 10, 99, 5. Let's make this 101. So if I inserted 100 in here, I think the prescribed algorithm would be put it here and then shift 99 over. But then the problem is now 99 is below 5. So this doesn't work. Also, if you're starting to say something like, well, I just go find the value closest but beneath it or whatever, we're talking about linear performance, right? If I have to go all the way down the tree to find... If I have to look at every value in the tree, I'm starting to talk about linear, which is not good. We want to do it in log. All right, what do we got? We got some good stuff. Cook it. I got no clue. Good. I like the admission. It's not even an admission. It's you're communicating, and that's good. There's got to be a number 2. Sometimes, if you're number 1, there doesn't need to be anybody else. So 16 would be 8's child, and then we would swap. 16 would be 8's child. So we're saying put 16 here. All right, if you guys want a hint 2, there's your hint number 2. Put 16 there. But then how did we know to put it there? How fast is finding that spot? Because where would I put the next value? What if I put in 19 or 5 or -1? Where would the next one go? So how do you find that spot? And how fast is it to find that spot? How did 8 end up on the right of 17? Because I drew it that way. It doesn't matter. The heap order property only states that every node's key should be greater than all of its children. So thus, the highest key is in the root position. For this, would you put 100 below 101, where 5 is? No. Yeah, the idea of like kind of inserting it midway, like this idea that we had earlier where you find a spot to insert it, is good in the sense that it maintains completeness. But the problem is that shifting right is n time. Right? So like if I put in the new highest value, in fact, yeah, that's the easiest counterexample, is if I put 18 into this, I'm going to have to shift the whole thing back, and in doing so we'll incur linear time, which is too slow. Okay, so then after I insert 16, it's not in the right spot. So what I'm going to do is who is it going to be at odds with, right? It's all of its ancestors. So basically what we have to do is, like I said earlier, in a max heap, if you start at the root and look down to a leaf, you should see values in descending order. So what I'm going to do is I'm going to swap it with its parent. And so now, let's get our eraser tool, which is where? Gradient, blur, stamp, brush, spot healing, which I tried to use last time. Crop, object, rectangular. How do I erase? Eraser tool. Oh, that is an eraser. Wait, what? What? Huh? Yeah. Go. That's a pen, yo. Eraser tool. This is cool, but I want the eraser tool. Okay. Let's do it live. When in doubt, just color white on top of everything. Okay. So now 17, or no wait, what were we in? 16? I almost said installing. 16, and then we had 8 down here. So we popped it up. Then we look at its parent and we say, hey, are you bigger than your parent? And it's not, it's smaller than its parent, so we're done. So, how fast was finding where to put it? So where do I put my next one? I'm gonna get a new slide here, or a new page, and we're just gonna do another one. Let's do 95, 20 or 32, 23. Let's insert. Well, let's just put 15 in here, because I'm not going to do a whole bunch of insertions, because that's going to take forever. Especially since I don't know how to erase. Just set the pen to white. Oh, yeah, see, great minds, right? 1. Okay. 16. 5. So what if I'm going to insert 100? What if I insert 100 in here? Put 100. Where do I put it? Whose child will it be? And which child of that node? So think about that while the stream catches up. I'm going to draw some circles. Because we love circles. I don't know why I spaced everything so tightly. Well, that was just shabby, wasn't it? Not that any of this is. I just want it to be legible. So where does 100 go? So 100 goes here. Yes! Tyler gets it. So what we're going to do is, if this thing's in an array, we have these are the indices for the array. 4, 5, 6, 7, 8, right? And so when we put in our new thing, to find the next spot that would keep the tree complete without having to do all this shuffling around, we just insert it at position size, which will be 9 for this one, right? So we had 1, 2, 3, 4, 5. We had 8 things in the tree, so I just inserted something at size. And yeah, we're good. Remember, this is dynamic array, so it'll just double every time I need more size, which incidentally will be when the underlying heap gains a new layer. Math. Okay, so, but 100's down here at the bottom and it should be at the top. So I'm going to compare it with 15, and I'm going to realize that, oh, what? No. Okay. I'm going to get rid of this. So now 15 will come down here, 100 will come up here, and then I'm going to compare it again. Then I look at 32 and 100. Well, 100 is bigger than 32, so you don't belong there. So now this is 32. It's going to start to look like my actual whiteboard. 100, and then over here, we'll compare it to 95, and then compare it to 95, and then swap a row, 95 and 100. So it started at the bottom and it bubbled up. How long is this going to take in the worst case? Well, how long does it take to find the spot where it goes? Constant time, because we have the size. We're just saying, boop, pop this in the array at this index. Constant time. 15's right child? Yeah, it's fine. 15's right child. Oh, yeah, that was, you guys were guessing. Yeah, 15's right child. Excellent. Yeah, I was like, what's wrong with 15's right child? The delay. Right, so inserting it at that position, constant time. So then, how long does this walk take? Well, this walk takes log of n. How do I prove that? Well, the quick proof of it is if we define a complete tree as being a perfect tree plus one layer, a perfect tree, by sort of definition, has height of log n, where n is the size of the tree. So we have a complete tree is log n plus 1. So we're doing n plus 1 hops, or, sorry, log n plus 1 hops, or log n swaps. And swaps are constant time. So I'm doing 4 swaps. And these aren't linked structure swaps, because those suck. These are just array swaps, which you've done plenty now, which is, oh, okay. Like, for example, the first swap I did will be like R or T equals R for, well, 43. What, my hand just kind of like has its own mind. T equals R4, R4 equals R7. And then finally down here at the bottom, R7 equals T. That's constant. That's 3. So constant time to find the bottom, constant time to, or logarithmic, and then I'm doing logarithmically many constant operations. So my NQ is logarithmic. How do I do a DQ? I will tell you that now that we've done red-black trees, you might start hyperventilating when I start talking about removals. That's a reasonable response at this point. Like, removal is just kind of between linked lists and red-black trees. You have now a response that's like, oh. Now remember, what node are we going to remove? Always, what node are we going to remove? Because this is a priority queue. We're going to dequeue the node with the largest value, which means that when we write this removal or the dequeue, we are going to remove the root. So we're going to remove that root. What do? It's not hard, so don't freak out. Just think about it. It's actually okay. And follow the same thing. Fix the completeness first, and then deal with the values. It's very similar to the strategy for in-queue. And we want to do it in log time. And then we're going to do the would you rather. Yes, when you implement a heap when you implement a binary tree in an array, the array at 0 index is not used. It's just null or blank or a default value. Move the bigger one up. Move the bigger one up is a common strategy. But then what happens to your complete structure if I move the bigger one up? That actually works for this tree. It doesn't usually work though. That's funny that it works for this tree. But if I made this 71, moving the bigger one up would not work. Because what would happen is there would be a hole here, and my tree would not be complete. So if I removed 100, so we're removing 100, and I moved 95 up and then 71 up, there'd be a hole and my tree wouldn't be complete. Maybe remove the root down after swapping in removal. Swap root with final index, remove the final index, and restructure. Swap root with the final index. What do you mean swap it with the final? You're close. All right, swap 100 with 15. Delete 100. Now 15's at the root. Then what? 15 is not the largest value in the tree. You guys are so warm though. Oh, like, ooh, like, oh, I can't even. I'd be too hot in this hoodie with how close you are. And then swap the root down. Yeah. All right, so that's pretty much it. Good, congratulations, Skyfugel. Oh, I know who Skyfugel is. Okay. Using your profile icon, cross-platform. So we delete 100, swap 15 into its spot. So here's what we're happening. Basically, all we have to do is R1 equals, and then R size. That's all that is. So now 15 comes up here. This spot down here goes away. It's gone. And now, so the tree is complete again, but now the key values are messed up, just like with the in-queue. So then we trickle it back down. So we bubbled up for in-queue, and now we're going to trickle down or push down or whatever you want to, I don't know, gently float like a tree leaf. How do we get 15 to a place where it belongs? My secret idea is revalued. So which one do we swap with? Skyvogel. It should be Skyflugel, because then that would be like a Skyvogel, which is bird. Skybird. Skyvogel. Yeah. Charlie gave away the game. He told me. He's like, I know who Skyflugel is. That's Char. Whichever isn't null. So who do I swap 15 with? What happens if I swap 15 with 23? Is that good? Are we happy with that result? Jules, are you happy with that result? Do you want in my lap? This is my real dog. Charlie's too sleepy. Jules plays fetch and, like, runs around like a freaking gazelle. Come here, you dummy. Do you want my lap? I think you do. I think that's why you're meowing at me. The larger child. Yes, Evan's got it. If I swap it with 23, then 23 will be above 95, which is bad, right? So you want to swap with your... In a max heap, you want to swap with your larger child. In a min heap, you want to swap with your smaller child. Because you want the new next best heir to ascend to the throne, right? So we want 95. Where's my pen at? We want 95 to be the new root, so we swap with 95. And we're just going to repeat that process all the way down. So as a result... Actually, I didn't need to do all that. I had a strategy for drawing these trees that made it really easy. So then 15 comes down one, and it'll come down again. And so it'll be 95 will be the new root. Then 71 will be the new left child there, and then 15 will find its home down there, right? So it's easy to bubble up because you only have one parent. So I just compare to my parent. When you're trickling down, you have to look at both of your children and basically pick the one of the two of them that would belong in your spot, which in a max heap is the larger of the two, and in a min heap it's the smaller of the two. What if one of the children is null? Then you only okay. Then you still have to, if there's a non-null child that's larger than you must swap with it. So oh no. So I'm trying to like draw on my trackpad. This is when where's my mouse? Okay, here we go. Suppose my entire tree, I've just deleted something and I have 10 and 15. Like this. Right? Even though I have a null thing here, I have to switch 10 and 15 because 15 should be above 10, right? So if one of your children is null, if they were in the correct order, then you could be done. All right. Cool. So that's how it works. So the in-queue algorithm is you put it down at the bottom using, you put it into the array at index size. Then you bubble it up as far as it needs to go. It might go all the way up to, if it's the new largest value, then it might go all the way to the top. but it might stop along the way. Then, for DQ, you make the new root, whatever was at the last position of the array, and then you trickle that thing down. That thing's going to most of the time trickle down pretty far, right? Because it had a bad value. If you're a leaf, that means that's bad for you. That means you're probably going to have to wait a while, right? So if you're taking a leaf and you're sticking it in the root position, you're going to expect it to trickle down a while. At least once. Sometimes not, but generally, yeah, at least once it's going to trickle down. So yeah. So you have 2 children. You compare with both of them. You only have 1 child, then you only need to compare with that guy. Correct. That's correct. All right, we're going to do, it's a little bit of a late would you rather, but we're kind of wrapping up here. So let's go over to let's back to the slides. All right, you can lift up to 3 pounds. Wait, did I do this right? I don't know why I'm so paranoid about my streaming today. You can lift up to 3 pounds telekinetically using your mind, but you can never lie. With your lying, you may fail to say something. You can say no comment, right? So if somebody says, do you like Jimmy? And you could be like, no comment, right? You could do that and not have to answer. So you're not compelled to answer questions, but you must speak truthfully. But you can lift 3 pounds telekinetically. And there's usually somebody's like, Baltimore. So you can move that 3 pounds, you can lift it telekinetically, but you can only give it, we'll say, 1 joule of energy. Not like this joule. This joule has a lot of energy. Look at him, he's massive. He's such a big cat. He's 20 pounds. When he's moving at all, he's got more than a joule of energy. He's also more than a 300. Or you can walk through walls, but you have to work at a dump. And nobody at the dump likes you. They're just kind of that. And you have to work 40 hours a week at the dump. It's actually not such a bad job. But it's also, like, probably pretty boring. It's an important job. What happens if you lie? You just can't. If you've seen the movie Liar, Liar, you just can't. You just won't be able to do it. Take the 3 pounds. Walk through walls. Walk through walls easy. I think there's a way to interpret walk through walls easy. Like, I already do that. I'll take the other one. Never lying would ruin relationships, I think. Oh, that's sad. You can have honest relationships. It's possible. It could ruin your life, Tyler. Wow. Melinda has, I think, inside information there. Isn't this an original? Yeah, most of these are originals, Cam. I haven't really changed the 341 ones, unless I add a lecture. How early can I retire if I walk through bank walls and steal the money from them? No, you must work at the dump for the rest of your days. You could be insanely wealthy, but you gotta work at the dump. Everyone in the world will compel you to work at the dump. No matter how wealthy you are, you could try to bribe them, but someone will always come and make you serve your time at the dump 40 hours a week. But it's an honest job, you know. It's boring, probably. All right, so let's dial up the poll. Continue getting this brain break. Last poll. No. Fast poll. Fast poll. There's probably better ones. Oh, straw poll. Straw poll's okay. It doesn't make me pick a category. Actually, you know what? Straw poll's better, I think, if I recall. Yes, this is good. Dump or lie? Kinesis. Oh yeah, we got it. Or walk through walls. You can also walk through. You can fall through the floor if you choose to do so. But when you hit the ground, you're done. I'm trying to play flight sims. Do you have any tips? They're awesome. War Thunder's a good entry. IP duplication checking. Yeah, we don't want anyone falsifying this incredibly important poll. This mission critical poll. We do not want anyone... Can work mean no. You're out there, you're moving, you're like, you're driving a little truck that takes the dumpster, actually, like the big dumpsters up to the landfill and pitches them in there. There's lots of jobs, but it's going to be a physically present, like moving stuff around job. You're not going to be a manager. You're not going to be a tech person. Good attempt at a loophole, but no loophole there. No, like with a flight stick. I agree. Those are good. War Thunder, there's a mode with a flight stick. There's a good $30 one. It's like Logitech. It has the ridiculous name. It's like Logitech Extreme 3D Pro. But it's like $30, and it's enough. I used it for like 6 years. Does it have to be a dump that is open? Yes. It has to be an active dump. Don't laugh. You know, the phrase active dump comes up a lot more when I'm teaching than I should probably be comfortable with. Do you hear a birdie? Do you hear a birdie, dude? You don't have to flat out lie. You can say something vaguely related. Yeah, people would be on to you. There's an excellent book series, Wheel of Time, where the only people who can exercise magical powers are women, and they, in order to be trusted, they all take a magically enforced vow to not lie. But they'll also, like, kind of dance around the truth sometimes. It's pretty awesome. I haven't even finished it. It's very long. I think it's significantly longer than the Game of Thrones. How fast can you move, launch things with your mind? 1 joule. 1 joule. If you don't know what a joule is is it 1 kilo moving 1 meter per second? Is that what that is? So depending on the size of the thing is how fast. Alright, good stuff. Alright, now I'm going to give you the riddle. Here's the riddle. For the class riddle. This is a fun one, though. And I'm, again, really bummed that we're not in person, because I usually give this at the end of class, and then I walk around, and usually at least one of you comes up with the answer, which is pretty beautiful. And I've even had somebody almost prove to me why it's correct. So then, one question you might have about... I'll bring up the irrelevant slide. Wait, what? Okay, so we got both of these down. InQ and DQ are logarithmic. We can find the minimum in constant time. You can actually do all of this same performance with a balanced binary search tree. All you have to do is maintain a pointer to the largest or smallest value, and every time you do an insert or removal, you update that pointer. And that's how you can do find min in constant time. So it's basically like a bookmark for the smallest value. So why are we using heaps? So here's the thing. Min heaps and max heaps are really good. They have really good performance for if I have a bunch of value, if I have a bunch of items with priorities and I want to put them into a priority queue quickly. So here's your puzzle. How do I do that? So I'm going to swap a Roodle back over to the Photoshops to write down your puzzle for you. This is such a good puzzle, and I'll look at chat and continue to BS with you guys while we figure out the puzzle. Okay, puzzle. That is a wonky P. Oh well. Okay, so the puzzle is given n values with priorities given n values with priorities, construct a priority queue in big O of n time. How do you do that? How long would it take with a balanced binary search tree? It would take n log n, because it's n inserts into a binary search tree, which would be log n time. So it's n log n. This riddle is fun. And then the second thing is so this is number one is hard mode. So this is a hard riddle. It usually takes people a little bit of a while. And then here's like rank S mode. Prove it. Prove that what you came up with runs in linear time. And that proof is kind of fun. But I will consider you an S rank success if you are even able to intuitively prove why it's linear and better than using a binary search tree. All right, let's see what we got. Going with the dump because the free money from the banks. Yo, what would you take, Natalie? Would you take the move up to 3 kilograms with telekinesis, but you can't lie? Or you take that over working at a dump? Really? I think you would.
Also, I looked up the word counts for things.
Word counts?
The entire Song of Ice and Fire series so far is 1.77 million words.
Uh-huh.
The entire Wheel of Time series is 4.4 million words.
Okay, so there you go. Wheel of Time is about 4 times as long. 3 times as long? 3 times as long.
What's
1.7 million words to 4.5 million words?
Close, yeah. 4.4.
Yeah, it's maybe like 2.5 times. It's long, but it's good. I haven't gotten through it yet, but it's already good. Would reread even to the point. Actually, I've read to the point I'm at twice now. It's just hard because it's so long, and then I forget what I've read. What's the question? Oh, I'm on the slides. I'm so sorry, guys. I wrote it out. I'm sorry. Given n values with priorities, construct a priority queue in big O of n time. So do it in linear time. Rank S mode, prove it. Prove it. Jeopardy music until he goes to Photoshop. Thank you. What's the book name? The first book is Eye of the World. Yeah, if you're stuck, if you're stuck inside and bored, it's a pretty good series, I think. I don't officially endorse it as a professor, but as a person, is being a person and a professor different? Yeah, a little bit. Just like being a comp sci individual and a person is a little different. He just doesn't care. I do care. I just didn't see the chat. Okay. So how do I do this? Okay, in chat, tell me when you're ready for a clue. Tell me when you guys are clue ready. any of you, just tell me when you're clue ready. Even if you're like super, don't give me a clue. I guess you could always pause the stream if you don't want a clue. I can't talk. Oh yeah, foundation books. I haven't read the foundation books, but I am aware of them. Well, it's an array still, right? Yeah, Tyler's getting there. Tyler's just going to give us our clue. Tyler's going to give us our clue. All right. So they're already in an array. So clue down here. Little clue. Secret clue. They are in an array already. So what do I do? I feel like we need recursion. Actually, we don't need recursion. No recursion for this one. So think about it. Here's a little bit more of a clue. If we were inserting all of these things into... So say I have a list of items. Putting them into a binary search tree is essentially the equivalent of sorting them, right? It puts them in sorted order. And the binary search tree sort of property of the key ordering property for binary search trees, where all the little guys are on the left and all the big guys are on the right, is a much more stringent property than just I am bigger than all of my descendants, right? So when if I just have an array of stuff already, by the way, this is getting into clue country. So if you're watching this, even if you're watching it live, you can pause and resume it, and I believe it will just pick up where you left off, which is why I prefer this over Twitch. Twitch will just take you back to live. I know you guys want to kappa your kappas and champ your pogs. Anyway, so if I have an unsorted list of items, if I put them all into a binary search tree, I'm essentially performing a sort, which is, you can actually, and I think you will definitely go into this algorithms, it can be shown that doing a comparison sort is in best case n log n. You can never come up with a faster algorithm. So, but we're building a heap, and a heap doesn't have as stringent of a thing. The resulting heap stored in that same array will not be in sorted order. So what do we do to those values in that array? Skyfugel is suggesting a lot of shoving. So find the biggest thing, shove it into another array as index 1, and then shove everything else into that array after it. Everything else, but that won't be a heap, right? We want to construct a priority queue. So it'll have the largest value and then just everything else in a crazy order. Or if you're suggesting I put the largest value in the new array and keep scanning over and over, then Rajan is correct. It would be n squared. Insert unsorted and sort as you go. Sort? See, sort is a little... I mean, I don't know what you mean by sort, because sort is like put in sorted order. But a heap, when you look at a heap, actually, if we go back to one of these things, if I draw the array for this mangled heap I have in here, it's 95, 71, 23, 32, 15, 1, 16, commas in here, 16 and 5. This is not sorted order. It's kind of sorted, but it's not sorted order. Shove it in a map. The answer is switching to IS. Is it using Brodel Q method? Wow, that's beyond me. I don't know what you mean by that. That's a Wikipedia lookup. Ding. Okay, here comes a stronger hint. Keep putting values in until you get to a value that's bigger than the max. No. Nope. I'm really excited about how much you guys are spitballing this. Just keep on going. So I have a Q, or I'm sorry, I have an index, or I have an array of values, and I want an array of values as a result. So how do I take an arbitrary array of values and turn them into a max heap? So if I had this right here, how do I take this arbitrary array of values up here and... Well, that's not an arbitrary array of values. That's the goal state, right? That's a max heap. How do I take... If I had jumbled all these numbers up, what's an efficient way of turning it into that? So say I gave you, 23, 71, 1... or say 15, 1, 5, and so on, how would you cajole them into being a max heap? What's your algorithm for that? All right, now you're just making up stuff. Now you're just, Bolzano know what, Weierstrass immediate value is a thing, but I don't know what it is. So it sounds like a math thing. It's such a good day outside. It really is. You can probably hear the birds chirping through my... The windows are like right there. They're right there. Oh, it is getting choppy on the stream. That's a bummer. All right. So I'm not going to tell you the answer. I suggest you think about it. If you want the answer before next time, go look it up in your textbook. And that's fun. And go look up the proof. The proof's actually pretty cool. I'm sorry if the stream has been conking out on you guys. I can't control my internet, unfortunately. What's my stream health? I keep getting warnings. Stream status is good. Good thing walking outside is still legal. It is. Just stay away from people. Do stay at home. I'm sure all of you have friends and family who are getting up there in years or might be immune compromised and things like that. So please stay at home. Don't go to parties and stuff like that. I feel like comp sci students might be some of the easier demographics. I know personally I'm like, woohoo, I get to stay at home. Oh no. But yeah, it is still hard. It's fun to go out to eat, go to movies, and see friends and stuff. I do miss my friends. Is Project 3 effectively due next Friday? It is effectively due next Friday, but you may not turn it in on Saturday, or you will get 0 points. Right now, it's a little choppy. We use Tony Flow in the Majestic Masters of Mayhem method. See, now that's some math. It's bigger than floor size. Has anyone come up with it? Look at the size. It's bigger than floor size. Swap the values. Continue in the Ulysses. Colin's getting warm. Colin is getting very warm. He's almost completed hard mode. Let's go look at the straw poll. Ooh! 12 and 10. Not many people on today. Now that the novelty of online...
So I talked with Jeff. Is that what you're calling about?
Oh. Now that the novelty has gone away, I guess
Yeah,
it's...
that's what he said. Did you figure out...
I guess you guys are just... Or maybe going to watch it recorded. Alright. So... Yeah. Submitted after Tuesday, whether it still goes in the late folders. Yeah, I'll find out. Bradley, you might want to email me, though, because I will forget.
Yeah. All right, I'll see
Colin might have a fever then. No, Colin's fine.
I mean, there's no
If he has a fever, the only prescription is for more cowbell.
he's okayed it, so.
Alright, it's choppy. I'm going to call it a day, guys. I'll be on Discord for about 45 minutes or an hour, taking questions and stuff. I don't know why I'm getting all roboted and things, but
About it.
have a great day.